Stream. Oops, the stream. All right, hello everyone. Oh, yeah, you should mute that one probably. We're gonna get started in a moment here. We are just getting some stuff set up, so bear with us for one more minute. Thank you.
So my audio output is muted. My audio input should be on or off.
Your audio input on. Just actually leave yourself unmuted. I'm gonna unmute here in a moment when we're ready. And then what you can do is here's what we'll do. So click share and just share your whole screen. Probably. Yeah, it's fine. There you go. And you're just presenting from slides or whatever, right? Yeah, you should be good. All right, cool. So what I'm gonna do over here,
See if it shows up.
yeah. Once we kick things off, I actually don't see your stream here yet.
You don't. System preferences.
Oh, you have to allow the permissions. All right. By the way, if you're dialed in right now and you have a question, please drop it into the chat, and I will relay it to our presenter as we get going over here. Cool. Switch back to these for now.
Chrome needed a restart. Back.
All good.
Hello.
Oh.
My name is Anand. We are in the company construction.
All right, almost there.
The product is sent from
Vanta, V-A-N-T-A. We use it as like a compliance tool. So it has all sorts of settings, and we're going for like SOC 2 compliance. So it's
I have exactly
It's
the
handy.
same desk in my house.
because otherwise, how would you would have to go and figure everything out?
I was just thinking, you can get these from everything.
Yeah.
Yeah. It's like a vuln management platform, right? Or like CM or whatever.
Oh, you are?
This is
Yeah.
so it's actually relevant to this meetup.
Oh, there you go. And then once you have that in there, I should be able to see you pop up on here. Okay, cool.
Do you see like the slide?
Yeah, I see it. So what I'll do is I'll add you to the stream. I'll sort of manage it from here, and we'll be good. All right, so
I think we do another check. Do you still see the screen?
let me just double check. Yeah, I see it.
And it's
We're
like
good.
full screen and stuff. right?
Yeah, yeah. Well, I'm gonna put it in full screen in a moment here. Okay, so let me just tell people we're gonna get started real fast, and then we'll kick things off. Right?
Everyone, let me get started in a minute. So once you got your food, come on in. That's it. Cool.
All right. And let me just make sure this is unmuted, actually. Yep. Okay, everyone on stream, we're going to get started in a second here. So we are broadcasting to you live from the StepZen headquarters in Santa Clara, California. It's a nice sunny day. Thanks for joining us. So real quick, I'll just give a little thank you to the sponsors. So first of all, we are literally at StepZen headquarters right now. So thank you very much, StepZen, for hosting. As a matter of fact, Helen or Anant, one of the two StepZen people, would you like to say a few words about StepZen on the stream?
Oh, that'd be awesome.
Yes, come talk into my laptop.
Oh, talking. Okay, they really want to see.
You have to.
Me?
You have to tell. You can just talk. Just tell people a little bit about StepZen.
So first of all, welcome everyone, and it's awesome having all of you here. And it was a great honor when Randall, whom we know very well, said, Anant and Helen, can you host a meetup here? So it was great. What we do is we are security conscious, but security is not the first thing that comes to our mind. What we are really about is how do we help developers build out APIs that abstract away the data wherever it is. And the problem that we are going to solve is that people who come in, the front-end devs, when they want to build an immersive experience, really the lifeblood of that immersive experience is data. But the data is wherever the data is. And therefore you have a lot of friction saying that, look, I want this bit and I want that bit. How do I get there? How do I get it to perform and all that stuff? So we had a background in Apigee, and we said there must be a better way of building out those APIs. And that's what we're doing. In this case, the APIs that we're building out are GraphQL APIs. We enable developers to kind of build them simply. But then because the way they build it, when a request comes in, we're able to actually optimize it and make sure it runs very well. Around it, security is kind of the job number 2 after all of that is done. Because what's the purpose of having an API that leaks data and everything? And so we kind of think about what's the envelope around it. But at the core, we're trying to help the developers build really awesome, simply awesome performant APIs. So thank you very much.
Yeah.
Okay. Really, really lucky to work with people like Helen. And that's what keeps us excited.
Well, thank you for sponsoring.
Okay.
Also, if you haven't heard of Sneak, feel free to check us out. But basically, we are a developer security tool, and we make it easy to find vulnerabilities in your applications. So with the sponsorship stuff out of the way, let's get into things. So first of all, I would just like to say hello to all of you that don't know me. But my name is Randall. I actually work at Sneak, which is why I was talking about it a moment ago. And this is our first in-person meetup ever for the DevSecCon Bay Area chapter. So you are all the inaugural members. So thank you for coming. It's super cool. I wasn't sure if anyone would show up. So it's actually great that anyone came at all. It's really nice. But for those of you that don't know about DevSecCon, I'll just give you the quick recap. So DevSecCon is the largest DevSecOps focused community worldwide. So not just here in California or in the US, it's literally all over the world. It's actually headquartered in London, believe it or not. And there are 18 chapters, I believe. So they're in Germany, Brazil, California, the East Coast of the US, pretty much everywhere. And they also have global conferences that they do in person. And so it's like a total community organized event. If you want to join the community and learn more stuff about it, there's a Discord server, which I'm super active on. A lot of people are on there. And we have a dedicated Bay Areas channel in there now as well. So if you do want to go in there and just hang out, feel free to do so. There's also tons of other stuff that happens, like other events and things. So be sure to check that out. But basically, we pretty much get together once a month is the plan, and just have a cool presenter like our special guest today, who I will announce in a moment, to just talk about any really interesting development and security focused topics. So my specialty is I've been doing engineering and security for a really long time. And yeah, I just thought it'd be fun to share that with other people. Speaking of which, our special guest for today, for the very first inaugural in-person meetup, is Marino, who is the CTO and head of product at Occam. So I will let you take over from here, and I'm going to switch back to stream and make sure people can see you. But thank you so much. Move. And we're going to do it like this. Here we go.
Oh, perfect.
Okay. It's all you. So now I'm going to plug this into your laptop. And I will just be the DJ. Perfect.
All right. Well, thanks, everyone. Thank you for coming. It's lovely to have this opportunity to speak with everyone in person and online. Thanks, Randall, for letting me be a speaker, and it's exciting, and I'm very, very I'm thrilled about the conversation. I'm hoping it can be a conversation, especially small group here. If you want to jump in and ask a question, just do at any point in time. Thank you for the hosts at StepZen for hosting it. This is very, very exciting. So the conversation, although my talk's title is a little bit different, I will touch on that in a second. I want to start the conversation by building sort of like an intuition for the vulnerability surface of any application we build these days. And I'm sure most people who are listening to this are involved in building some kind of application. So let's think about its vulnerability surface. To kind of open up the floor a little bit there, what comes to mind? Like, what would, if someone were to ask any of you, what's a vulnerability surface? What would be your kind of first reaction to that word? Anyone?
Data input.
Yeah, like risk in input of data, right? Like, could it be stolen? That kind of thing. But applications tend to have like lots of different vulnerabilities. And this is, especially as folks that want to build secure applications, it's really helpful to think about, well, what are my risks? Like, what risks am I protecting against? What threats am I protecting against? So let's dig into this topic, right? If I think about the vulnerability surface of an application, these are the things that come to mind, right? So there's the code of the application, which, if it's written badly, is leaking memory, has buffer overflow errors. Then the code itself can create vulnerabilities that will cause someone who is interested in attacking my application to leverage that buffer overflow and attack the application. But then there are libraries, and there's the operating system in which my application is running. Typically, we call services in our application that we rely on. We may have some infrastructure. It could be hardware in a specific environment, or it could be virtual infrastructure in the cloud environment, or it could be the network. And there's another kind of important component, which is our applications don't live in like a silo, right? They're always receiving and sending messages out, right, as data, like API calls and things like that. So there's that component. These are all the external inputs to my application. And if any of these have problems, my application could potentially be vulnerable to attackers, hackers, et cetera, right? So there's the application code. And if you think about like specifically what could go wrong in the application code, and because we're trying to develop an intuition, let's think in like probabilities, right? So what could go wrong? Like, what is the probability of things going wrong in my application code? It's the probability of someone on my application development team making a mistake, right? So someone in my team was doing something, either they didn't have enough information about a certain step, or they just didn't notice some mistake. And those are the ways to kind of compromise the code of my application itself, right? It could be by mistake, or it could be that someone compromises the development environment of a developer. Like, so if I think about my personal development environment, someone could inject bad code into my application by making me click a phishing link and get my GitHub authentication cookie and insert code that way, or stealing my YubiKey and using that to like impersonate me, right? There are ways to, or like hitting me with a hammer and saying put bad code in, right? Like all of those would work. So that's kind of the vulnerability surface of an individual developer. And a typical application is built by a team of developers, right? So if we had to take a guess, how many developers on a typical application development team? My guess is like 10, right? It's like the whole 2 pizza team size rule, right? So we have 10. whatever is the vulnerability surface of one application developer, me, times 10 is the vulnerability surface of my application's code, right? And I represented that on the screen with that little orange dot, and it's little because we'll see how this grows. So it's the probability of 10 people on our team making some kind of mistake that will cause our application to become vulnerable. Okay, let's go one step further, right? So you have applications have libraries. Libraries also are built by people and teams, and those people also can be vulnerable to either attack, mistakes, compromise, hammer, etc. Right? So how many libraries does my application depend on? That becomes the next question. So I'm curious if someone wants to take a guess of like their application has how many dependencies?
I'm going to say 100.
100?
Yeah. That sounds about right for me. But.
Nice. I looked up some data, like Sonatype has a report, and they said it's 128. So let's go with that. I think it varies, depends on the language you're in, what is the typical kind of library size in that language, because I find like, Node.js tends to have smaller, but lots of libraries. Java, Erlang, other languages tend to have bigger, but less number of libraries. So let's go with this number for the sake of like building this intuition. So it's 128, right? Now, how many people could independently add code to each library? My guess is, this is a made up number, my guess is 5, right? If 5 people could probably push to some open source library that I'm depending on, right? So that means that 128 into 5, that's 640 people could do something in a library my application is depending on and cause my application to become vulnerable, right? Okay, so that's the probability or the vulnerability surface of one of these 640 people making some kind of mistake or getting compromised some other way by an attacker that would cause my application to become vulnerable, right? But applications run inside some kind of operating system. This operating system could be a container, or it could be a operating system installed on some hardware in some factory. Doesn't matter. Either way, there's an operating system. Someone had to take a guess of like how many packages are in an operating system image these days.
A lot.
Sorry?
50?
50. 50 is
like,
nice. It's more, I think.
Like, yeah, hundreds.
Couple hundred. So I ran a little test. I was like, well, what are common Docker containers? The Node Docker container is 409, Python has 426. But, for the sake of my pictures looking like pretty, I'm going to go with that 128 number, right? So let's assume it's 128, right? Fair enough. Like we saw some more. There are probably people doing like scratch containers and small containers who have less. But let's go with that 128 number. So now we have 128 packages inside my operating system. Let's assume the 5 developers again, right? So it's 640 developers that could potentially make a mistake or get compromised. And so my application could potentially become compromised, right? So now the vulnerability surface of my application is 1,280 developers, right? And we're assuming that the vulnerability surface of an individual developer is a constant in this picture. But there may be some vulnerability, some variability there. Some people are more conscious about security, some are not. But regardless, it's 1,280 developers could potentially make a mistake, and that would make my application vulnerable. So the corollary would be, if my application has to be secure, these 1,280 people must not make a mistake, right? That's how my application stays secure. Okay, let's take this a step further. In a typical, and I realize I'm belaboring the point a little.
A point though,
Yeah.
that if those libraries are used a lot, then they would have had more eyes on them, right? So it's not really, whereas your application is built by the 10 of you, whereas those, so just think, how would you what factor would you put out there that says that the security profile from those 1,280 is probably less than the security profile from the 10?
There's a lot of data around this now, especially over the last couple of years, as we saw a lot of these types of attacks. They're called supply chain attacks. If you want to kind of look up these reports that have come out. In fact, there was a link to one over here from Sonatype. This one, right? And I think there's one from Sneak a few days ago, State of the Supply Chain Security. And turns out, if you're willing to squint, turns out people in open source libraries make just as many mistakes. This idea that open source libraries get more scrutiny is interesting, but I personally maintain a project which has like 100 contributors now or 120 contributors now. And honestly, only a few people know where everything is. Most other people are, jumping in, jumping out. Yes, it's useful. It is like, especially areas that need special scrutiny, it is useful, but we're lacking certain tools around it. And as I go a little bit further in the stack, I'll talk about how that's changing. But it isn't like the current state isn't that open source automatically means more secure. There may be some correlation, but at least all the data I've come across, it's not very obvious, right? So I'm for the purpose of our intuition, assuming that that's not true. There is no such correlation. It's equal probabilities, but there might be. But as you'll see, it doesn't actually matter for my argument. So we've got like this 1,280 potential people that could compromise my application. Now let's think about like how many applications are running in a typical network. And let me define network in this context, right? This network might be the VPC in an AWS cluster in which your application developed by the 10 people is one of the applications. There might be other applications like your database, your some other microservice, etc. Right? So that's one kind of network. Another kind of network would be my application's an edge application, and it's running in some factory. And how many other applications are running in the same network boundary in this factory? Or to take another example, think about how many applications are running in your home Wi-Fi currently. Applications written by teams of sizes of 10, how many of those are in your home network currently?
For me, a lot.
Right.
A lot.
Right, but it is a lot. It is at least in my house, it's in the thousands. And yes, right, and those things of operating systems, etc. However, we'll take a very conservative number here and go with that 10 again. So I'm going to say it's 10 applications in one network boundary. This, I think, is typical of cloud systems, right? So in a cloud setting, you have some, you have a microservices oriented team culture, and you're building 10 different little microservices to serve your customer. They're all running in the same network. So now suddenly my vulnerability surface is maybe 10 times. Maybe it isn't. Maybe we're sharing the same operating system image, and so maybe it isn't quite 10 times. Maybe but it's in the range, right? It's between 1 and 10 of my 1280, right? So suddenly we've gone from 1,280 people could potentially make a mistake to 12,800 people could potentially make a mistake and compromise my application. And we could sort of discuss for hours whether this number is correct or not. But let me make a point. Stay with me for a few more slides, and it doesn't matter whether this is correct or not. What matters is the order of magnitude. We're growing by multiple orders of magnitude, right? That's the point I'm trying to make. Well, okay, so if I have 10 applications in a network and all of them have this type of vulnerability surface, approximately 13,000 people have to never make a mistake for my application to stay secure. Let's take this a step further. Well, modern day applications don't run on themselves. Like, they rely on third-party services. They call APIs into other things. This could be cloud APIs. This could be, messaging APIs. This could be lots of things, right? So how many other services or infrastructure does an application rely on? And infrastructure is usually available as a service these days, right? So especially in a cloud environment, my infrastructure is also an API call to, I don't know, EC2 or S3 or something like that, right? So I again made up a number here and said it's 10, right? So it's, it'll be these types of things. It'll be compute services. It'll be event streaming services like Kafka or RabbitMQ or something like that. It'll be data storage services like RDS or a Postgres service. It'll be network load balancers. It'll be the VPC environment itself. Protocol gateways of various types might be involved, like GraphQL gateway might be involved, right? Messaging systems might be involved. And now suddenly, if you assume this is 10, is it fair to assume that those services are also running 10 different microservices in a network of 10 services, right? Actually, I would argue it is a lot more. Like, take an example, like Confluent Cloud is not 10 microservices. It is probably hundreds of microservices run by thousands of developers. But we'll assume that 10 scale at the moment because that's the argument we're building, right? But if you start thinking about it, it's all of these things are services and they have big teams building it. And if any of those people make a mistake, let's say the network load balancer implementation at AWS has some bug, that could compromise my application running in AWS, right? And usually at this point, if I'm having this discussion with someone would point out, well, but AWS is this big company. They can't make a mistake. Like, how is that possible? Well, it turns out if you look under the covers, those teams look like our teams. Like, they're no different. Like, they're not different at all, right? They make the same kind of mistakes we made. Yes, they're a little bit more mature in their processes, but actually at this scale, this is the error here is insignificant, right? So at this point, I've run out of slide space, so I'm going to use a visual trick, right? So that green box is going to represent 1,280 developers, okay? So if I stay with my 12,800 into 10, I now have a picture that looks like this. That's the probability of my application being vulnerable. At this point, if you pause and you think, you ask the question, what is the probability of my application today being vulnerable? The answer is 100%, right? So, okay, that's not good. Like, how do I go tell my customers I've got a secure system? And actually, this point about like big companies don't make mistakes, well, this is just the last year, right? In the last year, all of these big companies made massive mistakes. Uber was like last week, like their entire infrastructure was compromised because they made some configuration mistake, right? So big companies make mistakes all the time. Those teams don't look any different than our teams. All right. Now let's look at like a relative situation, right? That little yellow dot was the risk because of our application code. That little green box was the risk because of our libraries and our operating system. That was the risk because of our application in our network, right? Other applications in our network, right? And this was the risk because of services we rely on. So if you look at this kind of relative thing, you start to wonder, can I, like every time I remove a service I rely on, I gain a lot in terms of lowering my risk. So is there a way to use the service but not include it in my vulnerability surface? That's the question you start asking looking at this picture. All right, so what is the fix, right? And now let's go back to our picture, and there's a lot happening, especially over the last few years, as people have realized this is the landscape, and we are running applications that are 100% insecure. What do we do to fix? And there's people are attacking this problem from lots of angles. So there's, Rust as an example. Everybody probably has heard about, we should, there was a tweet from the Microsoft Azure CTO last week or 2 weeks ago where he said, there is absolutely no reason to write a C or C++ application going forward. We should be writing all those types of applications that are highly performance sensitive in Rust. The reason he's saying that and everybody else is saying that and the company I work for is building in Rust is because Rust does something very specific, which is it removes a whole class of vulnerabilities from application code, right? So turns out, and there's a report from Google that talks about 70% of critical vulnerabilities in Chrome were because of memory unsafety in the Chrome code base. There's a similar one from, I think, Apple talking about Mac OS vulnerabilities, and that number is like 72, 73% as well, right? So just by switching languages, if you're in an environment that is heavily performance sensitive and your alternative was using C or C++, you can switch a language and you can cut down 70% of your probability of making a mistake in your application code, right? That's why everybody's talking about Rust. But if you're in a language that isn't performance sensitive, then we have languages that are memory safe. Go is a good example. Java is a good example, right? These things are, because of they come at a memory cost, but they have garbage collectors and things like that make sure that memory unsafety is not possible, right? Which is great. Okay.
But if the application code is such a small part of the security service, why bother caring about language?
Well, that is a very, very astute observation, because actually it turns out, if you look at the whole kind of risk profile, almost anything you do here doesn't matter in that big picture unless you address the big picture first, right? So like I said, people are addressing this problem from lots of angles. There are other things. There are code scanning tools now, right? SonarQube's example, GitHub has CodeQL, which looks at code and tries to find mistakes we could make, right? They're doing static analysis on the code and trying to find mistakes we could make to further lower down the surface of application developers making mistakes. Then there's the whole ecosystem of companies, including Sneak, that is focused on libraries and container images and operating system images. And what they're doing is analyzing the things we depend on directly, like libraries. There's, Sneak looks at our container images, Sneak looks at libraries and NPM, etc., to flag and tell you, hey, you're about to put a vulnerable thing into production. There's a bunch of projects there's the Salsa project out of Google. Open Source Security Foundation has put out a bunch of projects that do scorecard analysis of libraries and things like that. There's this company, ChainGuard and SigStore, their open source project, which is working on making it so that all libraries have signed attestations on releases that can be easily verified, which is further kind of putting control, guardrails around our libraries, right? For the longest time, the wisdom has been, don't use the Node and Python image I linked to earlier. Use a very, very small base OS image. Well, turns out you can't if you're in a runtime dependent language, right? If you're in a runtime dependent language like Node or Python, you need a base runtime and you need those dependencies. So you can only go get down to a few hundred. But if you're building in Go, you can build a binary that can run in a Scratch container. And at that point, the number of packages in your operating system is 5 or 6, right? It's a really small number. There's also a bunch of really nice image-related work coming out of that ChainGuard team. There was a Wolfie announcement last week. Yeah, it was. So if you're interested in application security, it's totally worth your time to look outside your code and look at all of this work around libraries and container images, because the impact is disproportional to security, right? Okay. And then there's Occam. Occam's the company I work for. We're an open source project. All our code is on GitHub. And we're focused on that box on the top. How do we trust the information that comes into my message, into my application, and the information that leaves my message at runtime, or leaves my application at runtime. And turns out if you can make all the information coming into your application encrypted, and all the information that's leaving your application encrypted, and you're only talking to authenticated identities, you can remove the trust you place in external services, right? So let me give an example. If you're running, let's say you're running a traditional web app. It has a load balancer at which you terminate your TLS connection. And then from the load balancer backwards are your internal microservices, right? And if I'm not wrong, typically most people are not doing any authentication, data integrity guarantee behind that TLS load balancer, right? Which means that all the 10, 20, 30 microservices in that environment and all the external services in that environment are all part of your application's vulnerability surface.
I have an interesting story to share there.
Yeah, go ahead.
When I worked at Okta, I was doing some identity and access management consulting for a large customer. And I flew out to their headquarters and spent a week with their architects, like reviewing things. They had a lot of questions around, specifically, they had everything behind a single like proxy, like load balancer, and they were terminating to a variety of microservices on AWS and trying to instrument API authentication like across all of them. And when I started talking to them, because this is like a really large financial institution, when I started talking to them and asking them some basic questions about it, I assumed, oh, maybe they're using basic authentication and they have some set keys or something like that. But what I had come to realize is that they actually had literally nothing. There wasn't even a VPC. There were just EC2 instances running this PHP application right out of like a var www folder, essentially behind an Apache web server. And they would send sensitive financial information to each other over a public AWS network with no authentication whatsoever. It was pretty crazy.
This is, sadly, I talk to a lot of people with these types of problems, and this is far too common, right? So we talk about idealized architectures, but real world architectures look like this, right? They're the easiest path to getting something working usually, right? And the easiest path to getting something working is terminate TLS at load balancer and then just let traffic flow, right? And so my earlier assumption that it's 10 applications behind is actually way off. In that financial firm, it is thousands of applications behind, right? That load balancer. So this is far too common. So that brings me to the topic of my talk, which is we need to think about application layer guarantees of data authenticity, data integrity, and data confidentiality. That is how we can get a control on all of that massive vulnerability surface that has to do with external services and infrastructure. And that's what we're focused on, right? That problem of messages sent and received over the network. And turns out, if you do that, your application's vulnerability surface, in my made-up example, can go down from 128,000 people making a mistake to 1,280 people potentially making a mistake. And turns out our friends at Sneak and ChainGuard and GitHub and all of these other companies are helping reduce and get control on that 1,280. So that's how we get to applications actually being secure by design. So let's dive into and look at a couple examples of how we do this at Occam, right? So Occam is a collection of open source developer tools to orchestrate end-to-end encryption, mutual authentication, identity and key management for application fleets. All right, so these could be applications in your cloud environment, in your microservices, or it could be applications in a factory or a hospital or something like that. And all of these things need credentials, right? So you need to say, hey, this thing is allowed to talk to this thing, or this thing has this set of attributes, and this is why it is allowed to talk to this other thing, right? So we need to think about giving everything a provable cryptographic identity. which means we need to give all of them keys. We need to think about how those keys are secured, where they are stored, how they are rotated. Similarly, we need to give all of these things credentials and think about how these credentials are rotated, revoked, etc. And then eventually, as an enterprise, we will have policies that will say microservices from project 1 are allowed to talk to microservices of project 2, but microservices of project 3 are not allowed to talk to microservices of project 2. Right? We need mechanisms to be able to do this at scale and yet do it in a way that is simple. That's the problem we're going after at Occam. So if you look inside Occam, and as I said, the code is open source, you can go check it out. These are all the things we're doing, and I don't have enough time to kind of touch on all these components. I will touch on a couple of them, but we're doing things like making it easy for any transport topology to have end-to-end encryption. We're making it easy for you to have end-to-end encryption from one private network to another private network through relays in the cloud that only see encrypted data, right? This is akin to, Signal on your phone sending a message to Signal on my phone through a cloud server that doesn't get to see or manipulate any of the messages. We've made that functionality available as a function call, right? Your application calls a function, my application calls a function, and we can just do that. We make it easy to manage identities. We allow you to store those identities in safe vaults that can be hardware-based or cloud key management systems. I already talked about credentials. And if you have large fleets of things, right? If you have that financial services firm has thousands of applications, well, someone needs to onboard those applications, meaning give them credentials. There are whole protocols that need to be written around how does an application become a member of a project? When does the application get kicked out of the project? How does that happen, right? So we're building all of these protocols. And then we, of course, that last point over there, we also plug into your human identity systems, right? So that last bullet point is about identity providers and policy providers. So one of the identity providers you can use with Occam is Okta. Another one is Auth0. Another one is Azure Active Directory. So human identities in enterprises and big companies are already, even in small companies, are already Google Workspace identities, or they're already established identities with established roles, and we just plug into all of that infrastructure. Okay, so now let me touch on one of the features. One of these features is called end-to-end encrypted relays for any application. So this is the scenario I'm going to kind of play around with. That black line on the left and the black rectangle on the left and black rectangle on the right are two different private networks. Think of it like data center 1 and data center 2, or VPC 1 and data center 2, right? That kind of arrangement, or factory 1 and data center 2, right? Something like that. And there's a client in one private network that wants to talk to a server in another private network. And in my example here, this is a HTTP client, curl, and an HTTP server in Python, but it could be any TCP client or server in this example. So we want these two things to talk to each other without all of their traffic getting exposed to the internet. We also don't want to put a proxy that load balancer on the internet that gets to see or manipulate that data. Because remember, if we insert that proxy, now I'm gaining the vulnerability surface of that proxy, right? So I don't want to do that. I just want my two little applications to talk from here to here. Yes, they need to travel over the internet, but that's just routing. They shouldn't be able to manipulate the data of my application. They shouldn't be able to see the data of my application. So that's what we want to do. So to do this, we need a relay in the cloud. And I'm going to illustrate this with a couple of simple commands. Here I run a command saying Occam node create blue. This is like a sidecar sitting next to my web server. I then tell that blue node to create a TCP outlet from that blue node at some address to my web server. So this side of the setup is done. then I say, hey, Cloud Relay node, please create a forwarding address for me. So this is like a, this is like a PO box, right? So I'm telling this machine in the cloud saying, hey, give me an address that other people can reach me on. And so we create a forwarder in the cloud by issuing this third command. Then on the other side, we create a sidecar next to our client. We call it the green node. And then we run this really long command. And I know it seems intimidating. And the only reason I've typed out these commands is because I wanted to illustrate what's going on. Actually, these can be just simple configurations, but it's helpful to be able to understand it. So here in this command, Occam secure channel create, what I'm doing is I'm saying, hey, create a secure channel from green through the Cloud Relay node via the forwarder for blue all the way to the blue node. And so with this single command, I did what Signal on my phone is doing with Signal on your phone, right? It's setting up this end-to-end encrypted connection through a Cloud Relay node. Under the hood, there's a lot of cryptography involved. We did a lot of tunneling of protocols, and I'll probably show that picture in a little bit. But as a developer of this application, all you had to do is type these few commands and run it next to an existing application. You didn't have to change at all, right? So that curl HTTP client and that Python server, no code had to be changed. So if you have an existing application in one private network and an existing application, another existing client of that application, another network, you can just run these sidecars. And you get this end-to-end secure communication through the internet between them without changing any of your code. Of course, if you're interested in changing your code because you want more granular control, Occam's available as libraries. And the first library we have available is Rust, but we'll over time have other libraries available.
Can I ask you a question?
Yeah.
So if you're just using the libraries and not like a proper sidecar,
Mhm.
are you doing that within the application process essentially? Nice.
If you use the library, you have to write the
Yeah,
application process. Now, you could choose to write a customized sidecar of your own using the library. That would work too. But yeah, you either want to be in process or a sidecar next to your process, depending on your scenario. And we have users who are on one end, they're running in Kubernetes, so they're running a sidecar in their Kubernetes pod. And on the other end, they're running in a tiny device. And so they're using the Rust library to run in an embedded device, right? So that's possible because we're at the core a library.
Does that replace your networking functions for like HTTP and other things then? Or is it like monkey patching like system libraries and things like that? Like how does it work, I guess?
A very good question. So this TCP inlet and TCP outlet pair, basically, so, and I wish I had a pointer.
You can see it there. It's just really tiny.
Oh no, now I have lost my ability to actually. Okay, so this if you see that little yellow box next to the green square, that's the topology was set up so that to the client that looks like the server in the local network, right? So it's like curl is curling to local port 7000, right? And because we're tunneling TCP traffic, we're carrying over the entire TCP traffic through this multi-tunneled end-to-end encrypted connection. But to the client, it looks like it's just a server running on localhost.
Can you pass a variety of ports?
Right. So that's a really good point. Did you say a variety of ports or protocols?
Ports, yeah.
Yes, you can pass any variety of ports. You can set up different connections to different applications. All of that is possible. You can also, underneath the transport of this end-to-end encrypted connection was TCP in this case, but it doesn't have to be. So Occam, and I probably have slides for this. Let me not dive into it. I will jump into it. So let's dig into like why does this work? Like what is it, right? So the first piece we needed to build is a secure channel primitive, right? This is like TLS, but a lot more lightweight. But it's built on a proven protocol. The protocol is called Noise Protocol Framework. There's like if you've heard of WireGuard uses the Noise Protocol Framework. There are other very popular deployments of Noise. We are also an implementation of Noise. So we didn't kind of invent the wheel here, but we needed a lightweight secure channel protocol. It couldn't be TLS because TLS has a lot of historic baggage, right? TLS is standardized for browsers and it needs to deal with all of that. All right. So we're in the business of minimizing vulnerability surfaces. It made a lot more sense to have like a tiny code base with very simple implementation of noise. So that's our secure channel design. There's an initiator of the secure channel. It does an authenticated key exchange using public key cryptography to establish a shared secret. Once the shared secret is established, then it's using authenticated encryption with AES in a certain mode, AEAD mode, to actually then send end-to-end encrypted data. The reason to choose something like noise is that the properties of the secure channel in noise have been heavily studied for protection against various types of attacks that secure channel protocols face, like key compromise impersonation, forward secrecy related attacks, et cetera, et cetera, et cetera. This is a full talk on its own, but we're using a proven building block to we've made that protocol easy to use and call like a function. That's all we did here, right? So there's an interesting kind of distinction to draw here, right? So typically, if you have a secure channel, and let's take TLS, and you have an underlying transport protocol, your guarantees of the secure channel protocol are as long as the guarantees of the underlying transport protocol, right? So the safety guarantees of TLS are as long as the underlying TCP connection. Well, we want it end-to-end encryption. We don't want the connection guarantees of data integrity and authenticity to terminate in the middle. So to do that, what we did is we built a tiny little routing protocol. So this routing protocol kind of looks like this. You have an app, you have a hop in the middle, and you have some target you're trying to get to. And in the message, it carries these routing information. So it carries, okay, my next hop is a TCP connection to this machine. The hop after that is a TCP connection to this other machine, and so forth. So this is like an application layer routing protocol. And the benefit of doing that is that we can then decouple ourselves. I wouldn't get into the details of this. But the point is, because we have this routing protocol, this can be any number of hops in any transport protocol. So I can describe routes in this that could say, take a message from a tiny wireless device, send it over Bluetooth as the first hop, then send it over TCP as the second hop, then send it over another TCP connection as the third hop, and then it'll reach its destination. So we can describe these like multi-hop, multi-protocol routes and send messages along that route.
The sender determines the route?
The sender determines or discovers the route in some way. So once we have this routing protocol, this application layer routing protocol, now if we take a secure channel and you put it on top of this instead of a transport protocol like TCP, you get end-to-end encryption, because as long as the intermediate nodes can do this routing. So that's how we're able to do end-to-end encryption in any arbitrarily hop type of scenario. And your application can describe it. So this is, it's a little bit of Rust code, but just focus on line 16 and 17, right? So line 16, I'm describing a route where I'm saying my route is TCP hop to port 3000, then TCP hop to port 4000, and then to some secure channel listener. And then I create a secure channel by saying Alice, which is an identity, create a secure channel along this route, and just trust whoever is on the other end in this case, right? So just that one line of code or two lines, including the route, allows me to do what WhatsApp or Signal or Zoom's encryption protocol are doing internally, but just calling a function, which means any application can add this to their application. And then on line number 20, I just use the channel. That's it, right? I send a message, and now that hello Occam message is going to get end-to-end encrypted and move through this end-to-end encrypted tunnel and get delivered. So that little command line example we saw earlier, that's what it was doing. Like the code for it looks exactly like this, except it's just adding some usability so you don't have to write this code. And it's exposed a raw TCP port saying, any traffic that comes from here, I'm going to encrypt it instead of hello Occam and send it down this channel. So under the hood, since you asked, like that inlet-outlet topology kind of looks like this. We've got multiple TCP connections. We've got a secure channel based on Occam routing inside those TCP connections that is end-to-end, and then we're moving HTTP data, which is actually TCP data, through this channel. But as a developer, you didn't have to think about any of this. You just either wrote a couple of commands or wrote a couple of lines of Rust code and it just worked.
So here's a quick question. Usually one of the difficult things I've noticed is like handling that initial key exchange. Since you're doing public key crypto, how do you handle establishing that initial end-to-end encrypted channel there? You know,
so that's what the noise protocol framework very clearly specifies.
I see.
Basically, that is a really good question. So essentially, over almost 30 years now, like 26, 27 years, we've seen secure channel protocols break many times over, right? TLS or SSL in its early incarnation broke several times. TLS 1.0 broke, etc. Right? Secure channel implementations for Wi-Fi related protocols, for Bluetooth related protocols have all broken. And so there has been a lot of work put in the TLS 1.3 community and in the Signal community around making secure channel implementations really, really robust. So the author of the noise protocol framework is also the author of the Signal protocols in Trevor Perrin. And so those papers have, they specified a protocol. They've now gone through formal proofs and they've gone through a lot of study by academics around their robustness. So instead of us inventing some new handshake and making a mistake, it's very, very wise now to just build off of Signal and gives you, off of noise and rely on that. So that's what we've done. Okay, and now I'm going to start concluding very quickly. Where are people using this might be a question that comes to mind. So I'll give a few examples, right? So this is a SaaS application. I wouldn't name them because they're still early development, but they're a cloud-based SaaS application. They have many enterprise customers, and as a user is going through clicking buttons on their SaaS application, they need to reach into enterprise databases and fetch data out of them and display it to the user or manipulate it, right? And this data is living in an enterprise like traditional data center-based Oracle DB, right? So they need to, from their cloud SaaS, reach into these private networks and manipulate the data. And we were able to give them the ability to do that with just a few commands run here and a few commands run here, rather than this being a multi-year project for them around how they do this integration, right?
What's the biggest long pole for you getting it through the security group to approve this? In the sense that you're clearly not the traditional VPC architecture or whitelisting architecture or anything like that. Right? So you're imposing kind of a new virtual network, right? So are the enterprise security teams set up to understand this and approve for a SaaS application to connect to the database?
Very, very good question. So if a SaaS application is connecting to the database, the connection is going from the SaaS application into the enterprise, and that's where you hit a firewall, right? So the firewall, the IT admin of the enterprise says, well, I'm not going to allow you to expose a port on the network, or it'll be a long, kind of months-long approval process. In Occam's case, there is no port to open because we run a sidecar next to their database, which makes an outgoing connection out to a relay in the cloud. We run a sidecar next to the SaaS application, which also makes an outgoing connection to this relay, and they just talk. So there are no ports to be open. No one needs to, because the risk with opening ports is the moment you open a port, if you're a big enterprise, you get all sorts of attackers trying to do denial of service, get through those ports, etc. And in this setup, there's no ports to open.
Who runs the relay?
That is, so Occam's open source. You can run it yourself. We also
But you
offer.
then have that security thing you have to be okay with that relay.
Yes, the relay needs to run in an environment that can scale and handle. So it's like it needs to run on the internet network, right? So it's a cloud service, and in our case, we just offer that as a service. But you could also just run it yourself in like some cloud EC2 instance, and it will be safe because it doesn't get to see any of the data, right? So it's just transferring. So the worst thing you can do with it is denial of service. You can't see or manipulate the data. All right, so that's one example. Another example is someone's building a edge compute and data platform. They're a serverless engine. They're building a global edge compute and global data plane, and they have a control plane engine control plane that is running in the cloud, and they have these edge planes which are hundreds of them spread across multiple data centers around the world, and they need secure communication across this like mesh of things. And so they're using Occam to trustfully communicate between this central control plane in the cloud and their globally distributed edge network. This is a completely different example. This is one of the largest pharmaceutical companies in the world, their diagnostics arm. They build machines that look like this, right? And these machines are running, they collect samples and analyze them, like human fluid samples of different kinds, and analyze them, and they're running inside like a hospital or a lab or things like that. And traditionally, that lab did not have internet connectivity, right? So this machine, which is a multi-million-dollar machine, has absolutely zero security built in. There's no authentication, no authorization, nothing. It's built for a time where that was not a thing. And so it's running in some network. If you pay attention to the kinds of attacks that have happened against hospitals over the last few years, it is trivial to breach hospital networks. So the need they have is they need provable identities in these machines. This data that they're gathering is used to do like all the COVID-related pharmaceutical analysis was based on data from them, etc. So they're very, very worried about manipulation of that data, and so they need a source of like they need authenticity in the data, right? And with Occam, they can build it very, very easily. So that's what they're doing, and they're putting Occam inside these machines, and they have a cloud service where they're collecting all this data. This is another example. So you remember we talked about this like multi-hop routing protocol? Well, it turns out you can just route it into Kafka, or you could route it into RabbitMQ, which means you can have end-to-end encryption through Kafka or through RabbitMQ. So when your data lands inside Kafka or RabbitMQ or some other messaging or pub sub service, it is encrypted. And so the use case this customer has is they are one of the largest Kafka as a service companies, and they have customers who have GDPR requirements in the healthcare and the financial markets that say, delete the data in X years. And if you've ever dug into the architecture of log structured databases and how they work, essentially anything that gets written gets partitioned and copied and replicated and stored, etc., in so many places. This requirement that it should be deleted is incredibly hard to meet, right? But in our case, they're able to move this encrypted data to Kafka, so they benefit from the scale that Kafka brings in terms of collection of the data, but the data in Kafka is encrypted, and so to meet this requirement of delete the data after 7 years, all they have to do is throw away the keys, right? And now there's encrypted blobs sitting in Kafka somewhere. That doesn't matter. So that's why they're leveraging Occam. This is a financial services firm, a very large bank. They have and I've seen this pattern in a lot of large companies as well. They have thousands of AWS cloud accounts inside their enterprise. And inside each AWS cloud account, which is typically managed by one team, there are lots of microservices. And so they now have this need of services in cloud account 1 need to read services in cloud account 2 over the internet, And so they almost need like a multi-cloud, multi-account, multi-AWS account mesh, right? And with Occam, that's really easy to build. All you do is put all of these sidecars, and then we manage kind of the credential and authorization. So that's what they're doing with this. So now to kind of conclude my talk, I think there's something unique happening with this group of companies. This group of companies are making it possible to build applications that are truly secure by design, right? So what does this term secure by design mean? To me, this term secure by design means applications that have massively smaller vulnerability surfaces because during development, they considered all of these ways in which the application could become weak, right? So we're talking about applications that have tiny vulnerability surfaces, tinier than this. And so, my way of thinking about all of these companies and projects and standards is that they are building this like new category of application development tools around building trust in application data. And I'm very, very excited about this development. But this is how we do this thing everybody keeps telling us to do, right? There are books written on this topic, like build secure by design applications. But how exactly? Like the probability of my application being insecure is 100%. Like how do I solve that? Well, you do that by massively cutting down on the vulnerability surface, and we need good tools for it, which are now emerging. This is how you shift left, right? This is how security moves into development. This is how you zero trust, right? Like the whole zero trust thing has become a buzzword. But what does zero trust mean? Zero trust means don't implicitly trust all of these dependencies. Authenticate and verify everything, right? Authenticate and verify your libraries, authenticate and verify your container images, authenticate and verify all messages that come into your application or leave your message or leave your application. So zero trust is all about control and identity-driven verification of everything, which is what these tools are enabling. So if you're interested, come check out Occam on GitHub. Thank you all.
Thank you.
Why Occam spelled with a K?
So Matt, who is the CEO of the company and the founder, I joined a few months in. He was on the America's Cup sailing team for several years and was like a professional sailor for a long time. And his role on that team was instrumentation of those boats. So he was building instruments to kind of measure performance and things like that. And during that, he met a person who built those types of instruments. That company is called Occam Instruments, and their spelling was OCKAM. And that person's passed away now, but it's a nod to that earlier company.
So what are the biggest security issues you see like outside of this? Because obviously like the scope of vulnerabilities as you sort of went through is like truly massive, and this covers one big portion of it. But what are the things that you all personally see day to day, like from your customers, I guess?
Well, I think the biggest thing is it's not most people, right? There's teams at Google or Square or they're companies that are kind of the bleeding edge of the security problem, which are in a completely different kind of era, right? They're in like they're several stages ahead from your typical customer. Your typical company has no authentication. It has weak passwords. They've not adopted two-factor authentication. So they're still just dealing with like very, very baseline, make the passwords better, stop phishing, stop ransomware type of threats. And the vectors to all, like, that's how attackers come in. But then all of these other vectors is what allows massive compromises, right? So I don't know if that was an answer, but like what I encounter typically is someone way behind in this journey. And so I think we as a community that I think is talking about this like developer-oriented security practices. We as a community have to teach a lot of people about how to build secure applications, because I think it's like for most people, it's still security is still a after the fact activity. You have we have to move from security products bought by the IT team and the CIO to security being a part of the product, building secure products. Like we need to build secure products from scratch, secure by design. And that's the transition I think we are on. And I think the moment is right. There was a bill proposed, I think, in the US House a few days ago around open source security practices, etc. So it's like really, really top of mind for people at the moment. And I think that moment is right. There was this big White House executive order last year around security. So I think there is a big move, and that is causing a lot of people to transition. So that's the journey.
And one more silly question probably, but if you're actually instrumenting Occam at the application layer, so let's say you have like two Rust application servers that are talking back and forth to one another in different private networks. Assuming you just have a really basic infrastructure with like a single relay in the middle somewhere, how much network knowledge does the application engineer instrumenting it need to know? Do they need to know the full addresses for every hop along the way? Or is that something that's figured out sort of automatically in the SDKs?
So,
when you're building that array of all the addresses it goes through or whatever.
A really good question. So the SDKs can't do that, right? They can't do it because you need some kind of central place where this enrollment activity is driven by, right? And enrollment is about, let's say we all want to participate in a project and talk to each other, right? We're a group of applications talking to each other. Well, someone here has to start up some infrastructure and say, okay, I am now a credential authority. I will issue Randall a credential. I will issue this person a credential, this person a credential, and so forth. And well, how do if we are not yet enrolled into the same project, what is my basis of trusting Randall, right? So you hit these complex questions around how do you onboard a large fleet of applications, or even at small scale, even at the scale of 10 applications talking to each other, starts to get really, really cumbersome. And so that's where key management can become really hard, right? Identity management can become really hard. And that's where we run a credential authority. You can use the open source credential authority and run it yourself, but it's a little bit more work. But Occam's cloud offering, Occam Orchestrator, runs a credential authority for you. And it comes with ready-made enrollment protocol plugins. So you can say, hey, my application is going to get provisioned through Terraform. And so I need an enrollment protocol that would be convenient when my admin is provisioning Terraform either through a GitOps flow or a local flow. And so we give you that enrollment protocol and we say, hey, if you just add this module, you'll get your things enrolled when they turn on. But if your enrollment protocol is very different, which is I have a fleet of trucks to enroll, now you have a human that needs to go and touch the truck and say, hey, you're a node. But technically, there's nothing stopping from Occam, nothing in the Occam core architecture that would not allow for that truck enrollment protocol plugin to be adapted to. In fact, that was sort of related to my last job was related to IoT, and we did these very, very large, hundreds of thousands of devices IoT deployments in city infrastructure and airport infrastructure, etc. And there you typically have people going around installing these things and enrolling them. And that's a very different kind of enrollment protocol. But the core of the system, all the cryptographic protocols around authentication, authorization, etc., all are the same. This is just a peripheral thing that gets plugged in. Similarly, another peripheral thing you might want to plug in is, where are your keys stored? If I'm in a cloud environment, my keys should be stored in a KMS. If I'm in a tiny device, my keys should be stored in a hardware security module. If I'm on a MacBook, my keys should be stored in the secure enclave processor, right? So there are all of these safe places to store keys, and those are also plugins into Occam. And there's people in the open source community have already started contributing various types of Occam Vault plugins that help key storage.
Sorry, one other question too. If you're using a cloud provider like AWS, you mentioned there's a plugin for KMS, which is super cool. Would you recommend deploying things with Kubernetes using one of their like hosted services? I know there's a few, since you can have the sidecar and probably not have to worry about as much of it. Or like, what is the recommendation, I guess, to make this simple as possible? Like if you are building something for, so here's a better way to articulate it, I think. You have like this large AWS application that's running. So you have multiple microservices. Maybe some are like within a VPC on EC2 instances, just to keep it simple. Maybe there's some Lambda functions running to process certain things. They're sitting behind like an application load balancer, let's say. Would you recommend like migrating from something like this to putting everything into, oh no? Okay.
No, I think if that's working for you, that's a pretty good architecture, because like the amount of complexity that comes with running Kubernetes is enormous, right? Like it's complexity, it's vulnerability surface, it's chances of mistakes, etc. If your existing application architecture with EC2 machines is working for you, that's perfect. To add Occam to that, all you need to do is run a process in that same EC2 machine, right? So it's a OS level process sidecar rather than
I see.
Right.
Okay. I just assumed it was like a specifically for Kubernetes.
No, it doesn't have to be a container image. It can just be an operating system like process, right? And in fact, that command line that I ran was doing just that on my machine. It was running multiple OS level processes.
Is it fair to say it's like a WireGuard VPN centralizing to a central concentrated and kind of making network flattened into private networks?
So I think VPNs are designed for a different use case. WireGuard is a massive improvement over traditional VPN designs, just because the cryptography is significantly simpler. It's noise-based. Noise has a ton of proofs. But I think the use cases are massively kind of different in my view. I think WireGuard type VPN type infrastructure is nice for low throughput, teams interacting with each other type of activity. I don't think it's designed for these types of use cases, but I also don't have experience scaling that kind of infrastructure. But my hunch is that you'll hit kind of weird bottlenecks around it. In our case, you can have very simple point-to-point connections. Like there's no mesh that is needed. There is no like central thing. Like, so you can kind of choose the deployment to your scale. But at the same time, I will agree there are similarities in the design in that, WireGuard's choosing noise as the secure channel. WireGuard doesn't have this underlying routing protocol notion, which means that how do you move it over Bluetooth, for example, or how do you move it? Like, so there's like, I think that like very different kind of use cases. Yes, in a subset of use cases where you have a human on one end trying to reach some machine, you could potentially use a WireGuard-like thing. But I think we're just going after different types of things.
Also, the security engineer have this conflict, right? Like, where I choose something like a private link between two VPCs, right? Even though they are unencrypted, I have a choice of being unencrypted through a private link or encrypted or go over the internet, right? So there's that conflict.
Well, my knowledge on this isn't updated, but my understanding is the VPC private link capability will give you this VPC subnet and this VPC subnet, if far away, can talk to each other. I think it's fair to assume that that's implemented securely. I'm sure AWS would have done a bunch of work around making that secure. Probably uses TLS and things like that. But what's in that VPC matters, right? So if what's in that VPC is your single application and nothing else, then I think you have a small enough vulnerability surface. But if what's in that VPC is 10 applications here and 10 applications here. Now you have a massive vulnerability surface. And so now the benefit of using Occam would be that you're not assuming that any of those 10 can write data into your application. You're making sure that you're limiting down to a single machine. So I think depends on your topology, but if a private link works, sure, right? But it's like when you hit more complex scenarios, and realistically, I've typically seen VPCs with hundreds of things. It's very few people end up with a few things in a VPC, but who knows?
Well, thank you very much for the presentation.
Thanks a lot. Thank you for having me.
All right, thank you everyone on the stream.